In this video, we will go through the basics of how to build and train neural networks in Python using Keras and TensorFlow. We'll first see how to build and train a network on some simple data, and then see how to extend such a network by including one or several hidden layers. We will also discuss things like the learning rate, the batch size, the loss function, as well as how to save and load a network and much more. Finally, we'll see how to use an existing network for image classification and how to build networks for multiclass problems and networks with a continuous output. You can use different IDEs or text editors for Python, and I will here use Spider, but other editors should work just fine. If you're an R user like me, I would recommend to use Spider because it is very similar to RStudio. To be able to run the code as shown in this video, you first need to install the following packages or libraries if you have not already done that. Check how to install these libraries on your system. In Spider, you can, for example, install the following library like this. Once you have installed all these libraries, you will be ready to use the code in this tutorial. Before we start with the tutorial, I will first show how you can run a simple code in Spider and in Colab. To get a good start, I suggest that you copy the following code from my homepage into your text editor like this. In Spider, you can select which lines you would like to run and then click up here to run the code. Note that the training starts. On my laptop, the training takes about 10 seconds. Then we can print the optimized weights like this and use the network to predict. You can also use Google Colab, which is a free online platform that allows you to write and execute Python code in a Jupyter notebook directly in your browser. Make sure that the runtime type is set to Python. You can write and run the code in blocks like this. Although it works fine to run this code, we will get a warning here that suggests that we should define the input layer on a separate row. We then need to import also the input function and remove the defined input from this row and place it on the first row instead. If we run this code again, we'll no longer get this warning. The reason why we now instead get an error is because we first need to run this block to load the input function. Then we add the code for compiling and training the network. Note that I here set this argument to 0 to avoid a lot of printing during the training. In this case, the training took about 1 minute. We can now print the optimized weights. And use the network to predict. To learn something from this video, I suggest that you pause the video and write and run the code as shown. We will here start with a super simple example where the PSA level in blood has been measured on 7 patients that are known to have prostate cancer, and 7 healthy individuals. To train a network that can learn to predict if someone has prostate cancer based on a PSA level, we'll start with the simplest possible neural network, with only one input node that takes the PSA values, and 2 output nodes that compute the predicted probability that a person has prostate cancer, and the predicted probability that the person is healthy. This dataset is exactly the same as I used in my basic video about artificial neural networks. The first thing that we should do in Python is to import the following libraries or packages. From the following libraries, we import only the following specific functions or classes so that we can use them directly in the code. Then we create a one-dimensional array of the 14 PSA values, and an array with the corresponding labels for the 2 groups, cancer and healthy. Next, we convert these labels into ones and zeros, where the cancer patients are coded as ones and the healthy individuals as zeros. Since the healthy group is our baseline group, we should code it as 0. These ones and zeros will be our target values for the values in the output nodes. The output value in this node should be as close as possible to this target value, whereas the computed value for this output node should be as close as possible to 0. To be able to reproduce the results, we set a seed, which means that the weights in the network will be initialized with the same random values every time we run the code. To build a network, we use the function sequential. We here specify the number of input nodes for our network. Since we only have one feature or input node, we set this value to 1. For the output node, we use the sigmoid activation function, which will compute the predicted probability that a person has prostate cancer. The sigmoid function is usually used when we have 2 possible outcomes. Later on, we will learn how to use other functions when we have more than 2 outcome classes, or when we have a continuous output. This value determines the number of output nodes in our network. Since the probability that someone is healthy is simply 1 minus the probability that someone has cancer, we need only one output node. Note that I here use the argument input dimension, but you may sometimes see that the argument input shape is used. The argument input shape is more commonly used when we have more complicated inputs, such as when we use an image as input. Another way to set up the code is to define the input layer on the first row, and then the output layer on the next row, which probably makes more sense. But we then need to also import the input function. Anyway, for this video I will use the following code by using the argument input dimension. Next, we compile the network, where we define that we like to use an optimizer called Adam with a learning rate of 0.01. This kind of optimizer is the default optimizer, which is similar to the stochastic gradient descent method that we have covered in a previous video. Then we enter that we like to use the binary cross-entropy loss function, which is an appropriate loss function to use when we have a binary outcome, like in our case, where we like to predict cancer versus healthy. We will discuss the binary cross-entropy loss function in a few minutes. Let's run these lines to read in the data and to build the network. Once we have built the network, we can print the initial weights that are randomly set by TensorFlow. This is the initial value of the bias weight. And this is the initial value of the weight that is associated with the input node when we use the following seed. Try and change this value and run the code again. And note that you will get a different initial value of this weight every time you run the code with a new seed. Make sure that you run the code again with the following seed so that you start with the same initial weights as used in this video. However, if you do not get the same initial weight although you use the same seed as in this video, it might be due to that you use another version of Python. Note that you will then not get the exact same results as shown in this video. We will now train this network, which means that the network will update the values of these weights so that the network predicts as good as possible. To train the network, we use model.fit, where we here run 3000 epochs because our dataset is quite small. For larger datasets, you usually run much fewer epochs. By setting this argument to 1, we can track the training in real time, where the value of the loss function will be displayed on the screen after every iteration. If we set this value to 2, the value of the loss function will only be printed on the screen after each epoch. And if we set this value to 0, nothing will be printed during the training. During the training, the PSA values will be plugged into the input node, where the weights will be optimized so that the predicted values in the output node are as close as possible to the target values, which are 1 for the cancer patients and 0 for the healthy individuals. You should now run this code and note how the training begins. After we have trained the network, we can extract the optimized weights with the following function. This is the optimized weight that is associated with the input node. And this is the optimized value of the bias weight. If we would compute logistic regression on the same data with the following code, the estimated parameters in this model will be almost identical to the values of our weights. This means that this basic network is essentially the same as logistic regression. We can now use the network to compute the predicted probability that someone has prostate cancer given a PSA value of, for example, 2. To use the network to predict, we plug in the PSA value in the predict function and run this code. The output will tell us that the predicted value is about 43.5%. This means that the network predicts that a person with a PSA value of 2 has a probability of 43.5% of having prostate cancer. As we discussed in the video about artificial neural networks, such a probability is calculated based on the weights, the input value, and the sigmoid activation function. The predicted probability that a person with a PSA value of 2 is therefore about 43.5%. if you instead plug in the training data in the predict function and run this code and print the output, we should see these predicted values. For example, the predicted probability that a person with a PSA value of 3.8 has prostate cancer is about 99%. Remember that we previously created our target like this, where the cancer patients were coded as ones, whereas the healthy individuals were coded as zeros. During the training process, the network optimizes the weights so that the predicted values are as close as possible to the target values. This means that the network tries to minimize this binary cross-entropy loss function, where the predicted values are plugged in here and the target values here. We can compute the value of the loss function like this, which will result in a value of about 0.376. Since the output shape from the predict function is a two-dimensional array, whereas our target is a one-dimensional array, we need to use the method flatten to convert it into a one-dimensional array, so that the predicted values and the target values are stored in one-dimensional arrays in order to do this calculation. The value of the loss function can also be computed like this. This value corresponds to the value we see on the screen at the end of the training process. The smaller this value is, the better the model fits the data, which means that the predicted values are close to the target values. We will now calculate the accuracy of the model based on the training data. To do this, we need to convert these probabilities into predicted classes. If we use a cutoff value of 0.5, we can say that the ones with a probability greater than 0.5 are predicted to have prostate cancer, whereas the individuals with a probability value that is equal to or smaller than 0.5 are predicted to be healthy. We see that this healthy person is incorrectly predicted as having prostate cancer because its predicted probability is larger than 0.5, whereas this person with cancer is incorrectly predicted to be healthy because its predicted probability is smaller than 0.5. Since 12 out of the 14 individuals in the training data are correctly predicted, this gives us a training accuracy of about 86%. We will later see how to use a test dataset to compute a more realistic accuracy. We can also compute a confusion matrix, where we first set the predicted classes as ones and zeros, and then we compare that with the corresponding target values. If we run this code, we will get the following confusion matrix with the actual labels as rows and the predicted labels as columns. To make this table easier to read, we can create a heat map of the matrix with the following code. We see that 6 out of 7 healthy individuals are correctly predicted. Similarly, out of the 7 cancer patients, 1 is incorrectly predicted to be healthy, and 6 are correctly predicted to have prostate cancer. So far, we have used a cutoff value of 0.5, which gives us a sensitivity and specificity of about 86%. However, if we instead set the cutoff value to 0.2, this person will now be correctly predicted to have prostate cancer. But these two healthy individuals will now be incorrectly predicted to have cancer because their predicted probabilities are greater than 0.2. The sensitivity is therefore now 100%, whereas the specificity is instead about 57%. By using the following code, we can print the sensitivity and specificity for a range of different cutoff values, and create an RC curve that shows the relationship between the sensitivity and specificity based on different cutoff values. We'll now try to understand how the network predicts. But note that this kind of plot is only possible to generate when we have just one feature. These points represent the healthy individuals, whereas these points represent the prostate cancer patients. To draw a smooth curve in this plot, we let the network compute the predicted probabilities in the range from 0 to 5 with a step size of, for example, 0.01. Then we add the points, the curve, and some labels on the axis. If we run this code, we will generate a curve that shows the predicted probabilities by the network for a range of different PSA values. We will now see what happens if we extend the network to include one hidden layer with two nodes. We then add a line here, where we say that we still have just one input node, and that we now like to include the hidden layer with the two nodes. The output layer still includes just one output node. So, here is where you define how many input nodes your network should have. Whereas the last line in the sequence sets the output layer. Intermediate layers define the hidden layers. Note that we in this example use the sigmoid activation function to compute the values in the two hidden nodes, but you can try other activation functions that we will see later on. After we have trained this new network, the loss function generates a value of 0.305, which is smaller compared to our first simple network. This is expected because a network with a hidden layer will generally fit better to the data. If we extract the weights, we'll get the following optimized values for our network. If we plot the predictions with the curve, we see that the curve now takes a more flexible shape. This flexibility, which is provided by the hidden layer, allows the network to fit better to the data. Now, let's see what happens if we train a deep neural network with 20 nodes in the first hidden layer and 14 nodes in the second hidden layer. Before we train this network, let's define when we compile the network that we also like to see the accuracy on the screen during the training. Let's run this code. During the training, we can now also see how the accuracy is changing after each epoch. Note that the value of the loss function is almost 0 after 3000 epochs, and that the accuracy is 100%, which means that the network correctly predicts all individuals in the training data. If we now plot how the network predicts, we see that the network fits perfectly with the data because the curve now goes through every data point. We have, however, run into the problem called overfitting, which means that the network fits too well. Although it makes sense that the individuals with a PSA level of less than about 1.5 are predicted to be healthy, and that people with a PSA level greater than about 2.7 are predicted to have prostate cancer. It makes no sense that a person with a low PSA level is predicted to have cancer, whereas a person with a higher PSA level is predicted to be healthy, although the network fits perfectly with the data. We will later see how to prevent overfitting by using a validation dataset. We'll now see what happens if we change the seed. Remember that changing the seed will generate different initial values of the weights before the training starts. When we used a seed of 915, we got a perfect fit for the training data. If we instead change the seed to 1, the values of the initial weights will be set to other random values. And if we run this code, we will get a worse fit to the data. If we instead run the code with the following seed, we will get an even worse fit. So, this means that we need to try many initial seeds. As we discussed in the basic video about artificial neural networks. Just due to chance, the random initial values of the weights might result in that we get stuck on local minima. And if we are lucky, the random values of the initial weights might lead to that we find the global minimum, or at least a local minimum that gives a good fit to the data. Remember that we previously could print the values of the loss function during the training. We'll now see how to make the following plot that shows how the values of the loss function has changed during the training. This means that we will make a plot of these values. We therefore save the details about the training process in a variable that we call history. If we now run this code again, we can plot the number of epochs against the loss. From this plot, it is clear that the value of the loss function does not reduce much beyond 2000 epochs, which suggests that it would be enough to train the model with just 2000 epochs in this example, because the value of the loss function is then almost zero. If we instead run the code with the following seed, we see that the training has got stuck around a local minimum, because the value of the loss function is 0.24. However, if we increase the number of epochs to 22,000 and run the code, we may sooner or later reach a better minimum. We will now discuss the learning rate. To illustrate how this works, we set the random seed to 915, around 3000 epochs, which will generate the following plot. Now, let's reduce the learning rate from 0.01 to 0.008 and run the code. This will result in the following plot, where the value of the loss function is about 0.24 after 3000 epochs, compared to when we used a learning rate of 0.01, where the value of the loss function is almost zero. Using a learning rate of 0.01 therefore gives a much better fit to the data. By using a smaller learning rate, we have to run many more epochs to get the same accuracy, which is computationally expensive. Generally, the smaller the learning rate we use, the more epochs we need to run. So, why not then use a larger learning rate? Well, that may cause an instability in the learning process, where the value of the loss function may suddenly increase like this, and where the value of the loss function is now larger after 3000 epochs, compared to if we use a smaller learning rate. So, finding an appropriate learning rate is therefore crucial to find optimal weights for the network. An initial learning rate between 0.001 and 0.01 usually works fine. To understand the difference between one iteration and one epoch and how the batch size is related to the number of iterations, have a look at this video. In this video, I also explain how the weights are optimized. To illustrate the effect of the batch size, we'll here use a simple network without any hidden nodes. By default, the batch size is set to 32, which means that it uses 32 samples in each iteration. However, since our sample size is just 14, it uses all our data in each iteration, which means that one iteration is equal to one epoch when we train the network. So, the network plugs in all these values into the input node and computes the predicted values, which are compared with the target values to compute the loss function. The weights are then updated to reduce the value of the loss function. Suppose that we now change the batch size to 7 and run the code. That will change the weights a bit and will in this case result in a slightly larger value of the loss function. The optimized weights will also vary because the sampling of the batches involves a random process. By using a batch size of 7 means that the network takes 7 random samples and plugs in these into the input node and computes the predicted values based on these 7 samples, which are compared to the corresponding target values to compute the loss function. Based on the loss function, the weights are then updated. Then the network selects the other 7 samples and plugs in these into the network and computes the loss function based on these samples to update the weights. When you run this code, you will now see that 2 iterations will now be conducted in each epoch. If you run the code with a batch size of 1, you will see that 14 iterations are run in each epoch because we have 14 samples where each sample is used in each iteration. Similar to the learning rate, finding an optimal batch size is also important to generate optimal weights for the network. We'll now see how to save the following trained network with its optimized weights. Make sure that you first run this code. The simplest way to save the network is to use the save function. The file name should include the .h5 file extension. If you run this code, the file will be saved in your current working directory. To use an existing network that has already been trained, we no longer need this code. To load our saved network, we can run the load model function. We can now, for example, use the saved network to compute the probability that a person with a PSA value of 2 has prostate cancer. To display the model architecture of our saved network, we can use the summary function, which will tell us that we have 2 hidden nodes in the first hidden layer that are associated with 4 weights, and that we have 1 output node associated with 3 weights. The network has therefore 7 weights or parameters in total. To display the weights of the network, we can run the following code, which should show the values of these weights. Now, suppose that you would like to retrain your saved network based on our previous data. To retrain our network, we compile the saved network and train it based on our previous data. Note that the weights will be a bit different than our previous network, although we use the same training data because the initial weights are randomly generated. Now, suppose that we like to freeze the weights of all layers except for the weights associated to the output layer. We therefore first load our saved network again. We can then run the following code, where we set all trainable layers to false, except the last layer. If we run this code and print which layers that are trainable, we see that the first layer will be fixed, whereas the second layer will be trainable. If we run the summary function, we can see that 3 out of the 7 weights are trainable. If we now compile and train the saved network, we can see that these weights are exactly the same as our saved network, because this layer was not trained, whereas the output layer will have different values of the weights, because this layer has been retrained. The nice thing about retraining only the last layers in a network is that we may have trained a huge network that is really good for classifying, for example, objects in an image. If we then like to use the trained network to identify objects that the network has not been trained on, we can train only the last layers of the network so that we do not have to retrain a super large network from scratch. This is called transfer learning, because we transfer knowledge from one network to another. We can also modify an existing network. Let's create a new network, where we include all layers except the last layer. If we run these lines, we now see that we have only the first layer left, with its optimized weights. Let's add one hidden layer with 2 nodes to our existing network, and one output layer. If we check the summary, we can see that our network now has 2 extra layers. If we print the weights, we can see that our first layer includes the same weights as our saved network, and that the additional new layers have got some random values of the associated weights. Now, let's train this model, but where we like to fix the weights of the first layer so that we keep the optimized weights of the first layer of our saved network. If we now compile and train the network and print the weights, we see that our original weights are still the same, and that the network has optimized the other weights that are associated with the new layers. Note that this is just an example of how you can modify an existing network. This is basically only relevant if you do not want to retrain a super large network, because that might be computationally expensive. Remember that we previously saved the network with the file extension .5h. If we remove this, we will save the model in a so-called save model format, which will create a directory or folder instead of a single file in your current working directory. Then we'll load the network by instead using the name of the saved directory. To illustrate how to make use of a pre-trained network, we will here load the MobileNet, which is a pre-trained network for image classification of 1,000 different objects based on more than 1 million images. If we run this code, we see that this network has more than 4 million optimized weights and 1,000 output nodes. To test this network, I took the following picture of this little fellow who visited my garden. I then placed the image with the following file name in my current Python working directory. This image has 722 pixels in width and 745 pixels in height. This image is then loaded and resized to width and height of 224 pixels, which is the required input size for MobileNet. Next, the image is converted into NumPy array. Then the values in the array are normalized to values between 0 and 1. We will come back later on to why we normalize the input data. Then we use the model to predict and print the top 5 classes. With about 81% probability, it correctly predicts that it is a hare. With 18% probability, it thinks that it is a rabbit. In Keras, the Sequential API and the Functional API are two different ways to build neural networks. So far, we have only used the Sequential API to create a network. Based on the following data, this network consists of one input node, two hidden layers with two nodes in each layer, and one output node. We'll now see how to build the network by instead using the Functional API. We therefore need to import the following classes or functions. To instead create a network based on the Functional API, we will change this code to this code, where we here define the input layer like this, like we did as an alternative in the beginning of this video. Then we connect the input layer to the first hidden layer. Next, we connect these two layers to the second hidden layer, where X now represents these layers. Next, we connect these three layers to the output layer. Finally, we create the network by specifying its inputs and outputs. If we run this code, we will get the exact same network with the exact same optimized weights as when we use the Sequential API. The advantage with the Functional API is that it gives us more flexibility. For example, by using the following code, we can connect the input layer also to the second hidden layer. This is done by combining the input layer with the first hidden layer, so that all nodes in this combined layer are connected with the nodes in the second hidden layer. If you run this code and print the weights, you will see that the network now has optimized 2 additional weights compared to the previous network, because we now have 2 additional connections. These types of connections that bypass a hidden layer are used in the so-called residual networks. So far, we have used the raw data as input in the network, which happened to work fine in this case because we only used one feature where the values were quite small. Normally, we should always normalize the values before we train the network, because the network may otherwise run into problems during the training, since an appropriate learning rate is dependent on the values of the variables. One common way to normalize the data before training a neural network is to use the min-max normalization. For example, if we normalize this value, we would plug in this value here, the minimum value, and the maximum value of the input data for each feature here, and do the math. Similarly, we can reverse a normalized value back to the original scale if we plug in the corresponding values and do the math. Let's compute this in Python. If we run this line, we'll get the normalized data. And if we run this line based on the normalized data, we'll convert the normalized values back to the original scale. A convenient way to normalize the data is to import the min-max scalar class, where we initialize the min-max scalar object, which can be used for scaling. Then we use the fit transform method to scale the data. Note that this method requires that we first reshape our one-dimensional array into a two-dimensional array with 14 rows and 1 column. By instead setting the first argument to -1, the function automatically creates the number of rows based on the size of the one-dimensional array. If we print the normalized values, we see that we have got the same normalized values as the ones we previously computed manually. The difference is that this method returns a two-dimensional array, whereas this method creates a one-dimensional array. If we use the following method, we will convert the normalized values back to the original scale. So, from here on, I will only use normalized data as input for the network. We will here use our basic network without any hidden layers to see what happens if we instead use normalized data as input. The values of the weights have now been changed because we now use the normalized data. Note that we should now use the normalized values in the predict function. The computer predicted values based on the training data are approximately the same as before. To generate a similar plot as we did previously, we now compute a range of predicted values based on values between 0 and 1. Note that we now need to create a two-dimensional array of the X data, because our input data was a two-dimensional array, which is now expected by the predict function. Then we reverse these values between 0 and 1 back to the original scale, so that we can plot on the original scale. Previously, we used a network with just one input node because we had only one feature in our data. We will here see how to set up the code when we include a second feature, which is the age of the individuals. To include also the age, we add an array with the data. Next, we combine the two features into a two-dimensional array, which represents our feature matrix. Since our data is in the form of a two-dimensional array, we do not need to reshape it when we use this method for normalization. If we print the normalized feature matrix, we can see that both features now have values that span between 0 and 1. Next, we build the network where we now have two input nodes. If we train this network with the two normalized features, we will obtain the following weights. And the accuracy will be 100% compared to 86% when we used only one feature. Generally, the more features the network has to train on, the better the network will predict. We have so far used a network with only 2 outcomes, which means that we have a binary outcome. We will now have a look at a network that has more than 2 possible outcome classes. In this example, we will try to train a network so that it can predict 3 types of iris species flowers: Setosa, Versicolor, and Virginica. The iris dataset consists of measurements of the sepal length, sepal width, petal length, and petal width. We can find the iris dataset in the following library. We begin by loading the iris dataset. Then we put all the features into a feature matrix with the name X. If we print the first rows of this feature matrix and the feature names, we see that the first column contains the sepal length, whereas the second column contains the sepal width, and so forth. We can check the shape of X like this, where we see that the matrix or the 2-dimensional array has 150 rows and 4 columns. Next, we save the labels of the flowers in a variable that we call y, where the zeros represent the Setosa flowers and the ones represent the Versicolor, whereas the 2s represent the Virginica. If we run the following code, we can see that we have 50 Setosa, 50 Versicolor, and 50 Virginica in the dataset. Now we know the structure of this dataset. Next, we normalize the features by using the min-max normalization and split the data into a training dataset and a test dataset. We set aside 30% of the flowers for our test dataset and use the rest to train on. To make sure that we get the same proportion of the 3 species in the 2 datasets, we use stratified sampling. Also, to ensure that we get the same flowers in the 2 datasets every time we run the code, we here set a seed, which will allow us to reproduce the 2 datasets every time we run the code. Let's print how the training and test dataset look like. We see that the training data includes 35 flowers of each species, whereas the test dataset includes 15 flowers of each species. We will now train a simple network without any hidden layers. We can then set up the code like this. Note that to reproduce the results, we here need to set the following seed as well. We set the input dimension to 4, since we have 4 features. We can also write like this, because the second element in shape is equal to the number of columns or features in the feature matrix. The loss function that we will use is the so-called Sparse categorical cross-entropy loss function, which should be used if the labels are represented by integers. We will later see how to use one-hot encoding. If we train this network, we will get an accuracy of about 67% after 150 epochs, which is quite bad. Let's create a larger network where we now use 2 hidden layers with 10 nodes in each of these layers. We will here use the ReLU activation function in these layers. If we now run the code, we see that the training accuracy has now increased to about 97%, which is a large improvement. Let's calculate the accuracy based on the test dataset. We see that the test accuracy is about 93%, which is smaller than the training accuracy. This is usually the case because the network has not seen this data. The test accuracy therefore reflects the accuracy we should expect when we use the network on new data. We'll now see how to use the network to predict a new iris flower with the following measures. We then create a two-dimensional array and plug in the values in the same order as the features of the training data. Then we normalize the data and use the predict function. If we print the predicted values, we'll get the following values. Remember that we previously saw that the order of the species was Setosa, versicolor, and virginica. Since the maximum value is associated to virginica, we should predict a new flower as virginica. If you run the following code, it will automatically print the label virginica, because the argmax function will return the value 2, since the maximum value is located in the third element, where we find the label virginica in the array iris.targetNames. However, note that these values do not sum up to 1, which means that the values cannot be interpreted as probabilities, as we could when we had only 2 outcomes. To compute probabilities when we have more than 2 categorical outcomes, we can change the activation function that is associated with the output nodes from sigmoid to the so-called SoftMax function. If we now run this code again and print the predicted values, we will see that the predicted values now sum up to 1. The probability that the new flower is of type virginica is therefore about 50.4%. So, to compute probabilities when we have more than 2 classes, we should instead use the SoftMax function. We have previously used the Sparse categorical cross-entropy loss function, which is convenient and simple to use if our labels of the categories or classes are in the form of integers, as we had in the target variable for this example. However, sometimes you may see that the target labels have been one-hot encoded, which can be done with the one-hot encoder class. If we plug in our target variable here and reshape it to a two-dimensional array, which is required by the one-hot encoder, and print the encoded labels, we see that the Setosa flowers are coded as 100, versicolor as 010, and virginica as 001. This means that during the training process, when a Setosa flower is plugged into the network, its target values should be 100, because the network should be trained so that the predicted value is as close as possible to the value 1, whereas the predicted value for the other 2 species should be as close as possible to 0. Similarly, when a versicolor is plugged into the network, its target value for the second output node is 1, whereas the target values for the 2 other output nodes are 0. We then basically use the same code as before to normalize and split the data. The main difference in the code is that we no longer use the sparse categorical cross-entropy loss function. Instead, we use the so-called categorical cross-entropy loss function. So, use sparse categorical cross-entropy if your labels are in the form of integers, and use only categorical cross-entropy if your labels are one-hot encoded. There is no difference in the accuracy or model performance between the two methods, as both compute the same mathematical operations internally. The advantage with the sparse categorical cross-entropy is that it works with the integer labels directly, which will save memory since the data structure is more compressed. In comparison to the weights, which are optimized during the training, hyperparameters are settings that are set by the user before the training process begins. Selecting the best combination of hyperparameters can greatly improve the performance of the network. Finding the best set often requires trial and error, tuning, and validation. The following hyperparameters are things that we previously have decided before we started to train the network. Also, the type of normalization and the initial values of the weights may also affect the performance of the network. For example, in the previous code where we used the iris flower dataset, we used a learning rate of 0.001, which is the default value. However, we can try different learning rates and see if that improves the network. Similarly, we can try different batch sizes, the number of epochs, the number of hidden layers, and the number of nodes in each of those layers. We could also try different activation functions in hidden layers and different types of optimizers. But how do we know if a certain setting improves the performance of the network? Well, we should not focus too much on improving the accuracy based on the training data, because we may run into the problem of overfitting. And we should definitely not try to change the hyperparameters to improve the accuracy based on the test dataset, because this dataset should only be used once we have the final network that is ready to be tested. To find the best setting of the hyperparameters, we can split our iris data into training data that we use to train the network with. And then we may have, for example, 30% of the data as a validation dataset. We can then try a range of different settings of the hyperparameters on the training data and use the setting that results in the best performance based on the validation data. Once we have found a network that performs well on the validation data, we can combine the training data with the validation data to train our final network on. And then we can test how well the trained network performs on new unseen data, which is the test dataset. One problem with this method is that the optimal hyperparameters will be quite dependent on the random split into the training data and the validation data when we have a small sample size. Another way to do this is to use cross-validation, which means that we train and validate on the same dataset. For example, we may like to see if a certain learning rate improves the prediction by the network. We can then train the network on these 70 flowers and calculate, for example, the accuracy based on these 35 flowers. Suppose that this accuracy is equal to 90%. We then take these 35 flowers and use them as a validation dataset, whereas the flowers in the previous validation dataset is now used in the training dataset. These 35 flowers are still used as training data in the new dataset. We then train the network on these 70 flowers in the new training dataset and use these flowers to compute the accuracy. Suppose that the validation accuracy is 88%. Finally, we use these flowers as the validation data and the rest in the training data. Suppose that the accuracy based on the validation data is 92%. We can then take the average of these three values to compute the overall accuracy. This example represents a threefold cross-validation because we have created three different sets of data. Once we have determined the best hyperparameters based on the cross-validation, we use all the 105 flowers to train the network on, and use this final network to see how well it can predict the test data. Instead of using a threefold cross-validation as shown in this example, it is common to use a fivefold or a tenfold cross-validation for smaller datasets, like the iris dataset. This was our previous code where we computed the performance of the training data. Note that we no longer set a seed because we like to explore how different random initial weights affect the performance by running the same code several times. We will now import the following to perform cross-validation. We start to create the following function for building and compiling the model. Next, we replace this line with this line that uses the function we just created. Then we set up the code like this to do a fivefold cross-validation. If we run this code and print CV, we'll get the validation accuracy of the network based on the 5 different datasets. Note that these accuracies may differ a bit every time you run the code because we do not use any seed in this example. We can then compute the mean of these accuracies to check the overall performance of the network. In this example, I happen to get an accuracy of about 97%. Try and run the code a couple of times to get a feeling for how much the accuracy changes between the different runs due to the random initial weights. We can now, for example, see what happens if we change the activation function in the hidden nodes from the ReLU function to the sigmoid function. The average cross-validation accuracy will now be lower than our previous accuracy. I get accuracies around 94%. Increasing the number of hidden nodes in the 2 hidden layers does not seem to improve the accuracy. Changing the optimizer from Atom to the classical stochastic gradient descent will reduce the accuracy a lot. But if we change the learning rate and run more epochs, we'll get an accuracy of around 96%. So, as you see, there are a range of different things to tune on. It would be nice if we could automatically change the hyperparameters. I would then recommend that you have a look at the tool Grid Search, where you can automatically perform hyperparameter tuning. Anyway, after trying many different settings, these settings gave me the best validation accuracy, where I in most cases got an average cross-validation accuracy of 97.3%. Note that this network is quite simple, with only one hidden layer. Since the iris dataset is quite simple, it makes sense that the simple model performs better because it does not overfit. If you now train the network based on all the training data with the optimized hyperparameters found from our cross-validation, we get a test accuracy of about 98%, which is pretty good. As an example of a network with a continuous output, we'll here use some car sales data of similar cars but of different ages. These are the prices and ages of the 13 cars. If we normalize the price and age by using the min-max normalization, we'll get the following rounded values. Let's plug in the normalized data like this. Then we convert the one-dimensional arrays into two-dimensional arrays. We will now build and train the network. Our network consists of only one input node and one output node. When we have a continuous output, we usually use a linear activation function. Since we have only one input node in this example, we can remove this summation notation and write Z like this. If we plug in this expression here, we see that our network is basically a linear equation. When we have a continuous output, it is common to use the mean squared error as the loss function, where y is our observed normalized prices, and y hat is the predicted normalized prices by the network. After we have trained the network, we can see how it predicts the training data and compute the MSE like this, where price corresponds to the observed data and y hat includes the predicted prices by the network. To compute the MSE, we divide the sum of the squared errors by the sample size. The MSE value is in this example about 0.0059, which is the same value you will see on the screen at the end of the training process. If you print the optimized weights, we see that the bias weight is equal to about 0.83, and that the weight associated with the input node is equal to about negative 0.88. If we would use linear regression on the normalized data, we'll get approximately the same values as the two weights in our network. So, this simple network is basically the same as linear regression. Let's make a plot of the data and the predictions by the network, where we add blue points that correspond to the normalized price and age of the 13 cars. To add this line, we let the network predict the price of 100 values between 0 and 1, and draw a line based on these values. We see that the bias weight corresponds to where the line intercepts the y-axis when x is equal to 0. This can be interpreted as the predicted normalized price of a brand new car. The weight that is associated with the input node is in this case equal to the slope of the line, which can be interpreted as how much the price declines every year on the normalized scales. Now, let's create a deep neural network with 3 hidden layers. We add the hidden layers like this. Let's train this network and plot how it fits the data. We see that we get a bad fit to the training data. Let's train a bit more, where we instead run 3,500 epochs. We see that we now get a much better fit. Let's try to instead run 25,000 epochs. This will result in that we get a perfect fit to the training data, because the curve now goes through every data point. However, we have definitely encountered overfitting, because the curve looks a bit strange, and it makes no sense that the price suddenly should start to increase here, or here. Let's also plot how the training error is changing during the training. We see that the training error is almost 0 after about 20,000 epochs. Suppose that we also have set aside the price and age of 13 additional cars that we will use to validate the network with. To include the validation data in our previous code, we can plug in it here, which means that the validation error will be computed after each epoch in addition to the training error. Then we add the following line to see how the validation error has changed during the training. Then we run this code, which will now take longer time to run because the validation error will be computed after each epoch. While the network is training, note that the training error keeps going down, whereas the validation error stops reducing after around 3000 epochs and then starts to increase a bit. Once the training has been completed, you should see the following plot. We can see that the validation error starts to increase after about 4000 epochs, which means that the network starts to overfit. One method to avoid overfitting is to use early stopping, which means that we stop training when the validation error starts to increase. This means that we should stop training after around 3500 epochs. If we run 3500 epochs, we see that we get a quite good fit to both the training data and the validation data. The network is now more appropriate to use in order to predict new data because it seems to generalize well on unseen data. Once you have a basic understanding of neural networks, I recommend that you have a look at these videos to learn more about advanced neural networks. At the end of these videos, I show the Python code to build and train these networks. This was the end of this basic video about building and training artificial neural networks in Python. Thanks for watching.